In this video, we will be solving trig equations. And make sure you pay attention to the given domain in the problem. When you solve a trig equation, there can be one answer, there can be many answers, there can be an infinite number of answers, and there could be no solution. So always pay attention to the domain, which is all possible values of the input or the variable you're solving for. In this first part, our domain for theta is 0 to 2 pi. So when I try to find what theta can be, I'm thinking only between 0 and 2 pi, which is basically the unit circle. So in part A, where does sine theta equal 1/2? If you can picture the unit circle, sine theta equals negative 1/2 at 11 pi over 6, and also at 7 pi over 6. So theta is 7 pi over 6 and 11 pi over 6. And the next one, where does cosine x equal 0? Well, cosine is 0 up at the top, pi over 2, and down at the bottom, 3 pi over 2. So x equals pi over 2, or 3 pi over 2. In the next problem, it says to find all possible values of theta over the interval negative 2 pi to 2 pi, such that tangent theta equals negative radical 3 over 3. Now, our interval is different. The domain of this problem is now negative 2 pi to 2 pi. So we're not just looking at our normal unit circle from 0 to 2 pi, we're also considering the angles from negative 2 pi to 0. So first, let's figure out where on our unit circle do we have tangent theta equal to negative root 3 over 3. Well, that happens when the y-coordinate over the x-coordinate is negative 1/2 over root 3 over 2, because that's negative 1/2 times 2 over root 3, which is negative 1 over root 3. If we rationalize the denominator, that gives us negative root 3 over 3. So we're trying to find a place on the unit circle where the y-coordinate is 1/2 and the x-coordinate is root 3 over 2, but we need one of those to be negative. So it's going to have to be in quadrants 2 and 4, and a y-coordinate of 1/2 and an x-coordinate of root 3 over 2, that's going to happen at 5 pi over 6, where you have the coordinates negative root 3 over 2, comma 1/2, or also down here at 11 pi over 6, where you have the coordinates positive root 3 over 2, negative 1/2. In both of those cases, y over x will be negative 1/2 over root 3 over 2. So the places it happens in our normal unit circle from 0 to 2 pi are 5 pi over 6 and 11 pi over 6. But we also need to consider the angles between negative 2 pi and 0. I could also consider 11 pi over 6 to be negative pi over 6, and 5 pi over 6 is the same or coterminal with negative 7 pi over 6. So I actually have 4 answers for this problem. My final answers are theta equals negative 7 pi over 6, negative pi over 6, 5 pi over 6, and 11 pi over 6. In these next problems, we have yet another domain situation where theta is in the set of all real numbers. So theta can be any number from negative infinity to infinity that satisfies the equation. Cosine theta equals 1 at theta equals 0, but that's also 2 pi. If I make another full circle, it's also 4 pi, it's also 6 pi, and so on. And we also, if we swung around in the negative direction from 0, we could also consider that negative 2 pi. It could be negative 4 pi, negative 6 pi, and so on. So it's basically any even multiple of pi. So the way we represent this is we say theta can be any multiple of 2 pi, and we call that 2 pi k, where k is any integer. In the next one, tangent theta, or tangent x, equals 1. Tangent x equals 1 when you have y over x is root 2 over 2 over root 2 over 2. So that's going to be at pi over 4. And if they were both negative, that would also work. So in quadrant 3 at 5 pi over 4. But remember that we're talking about the set of all real numbers, so not just between 0 and 2 pi. If I add a half circle to pi over 4, I get 5 pi over 4. If I add a half circle to that, or add pi, I get 9 pi over 4. If I add another pi to that, I get 13 pi over 4. And I could keep going. So basically, if I start my first answer, if I consider my first answer to be pi over 4, plus any multiple of pi, because if every time I add a half circle or subtract a half circle, I'm going to get another possible answer. So I'm going to say pi over 4 plus pi k, where k is any integer. One more example like that, sine x equals root 3 over 2. Positive values for sine x are in quadrants 1 and 2, so it could be up at the top at pi over 3, or also at 2 pi over 3. But remember, there's more values than that. If I had a full circle to pi over 3, I would get 7 pi over 3. I could also add a full circle to 2 pi over 3, and I would get 8 pi over 3. So the way we're going to express our answer this time is x equals pi over 3 plus any full circle. So any multiple of 2 pi, so 2 pi k. Or x could be 2 pi over 3 plus any full circle, 2 pi k, where k is any integer. In this next part, we're back to a domain of 0 to 2 pi, so that's where we'll be searching for our answer. But we need to isolate our trig function before we can find the possible values of x. So in part A, I need to get sine x by itself. So I'm going to add 1 to both sides, and I get 2 sine x equals 1. Then I divide both sides by 2, and sine x equals 1/2. Now I go to my unit circle, and I think between 0 and 2 pi, where is sine x equal to 1/2? That's going to be at pi over 6 and 5 pi over 6. And those would be the only values between 0 and 2 pi where the y-coordinate is 1/2. In the next one, again, we want to isolate the trig function, so we want to get cosine x by itself. So I add 1 to both sides, and we get square root of 2 cosine x equals 1. Then I divide both sides by radical 2, and we get cosine x equals 1 over radical 2. I don't recognize that value from the trig, or from the unit circle, so I'm going to rationalize the denominator and see if that helps. So if I multiply by radical 2 over radical 2, we get radical 2 over 2. And now when I go to my unit circle, I know that the value of cosine is positive radical 2 at pi over 4 and also at 7 pi over 4. So those will be my answers. In the next problem, it says solve for x given that x that symbol means is an element of the set of all real numbers. So x is in all real numbers. So first we're going to isolate secant x. I'm going to add 6 to both sides. And we get 3 radical 3 secant x equals 6. I divide both sides by 3 radical 3 to get secant x by itself. And we get secant x equals 6 over 3 radical 3. I can simplify that fraction. 6 and 3 are both outside the radical, and they can both be divided by 3. This becomes a 1 and a 2. So we end up with secant x equals 2 over root 3. Now, it's probably easier for me to think about cosine. So remember, secant is the reciprocal of cosine. So I want to figure out where is cosine x, the reciprocal of 2 over root 3, which would be root 3 over 2. On the unit circle, cosine x is root 3 over 2 at pi over 6 and 11 pi over 6. But remember, in this problem, it says that x is in the set of all real numbers. So I'm going to represent my answer as x equals pi over 6 plus any full circle, which would be 2 pi k, any multiple of 2 pi. And x could also be 11 pi over 6 plus any full circle, so plus 2 pi k, where k is any integer. In the next part, we're going to be solving trig equations that are also quadratic. So we'll use a similar method to if I wanted to solve x squared equals 9. To do that, I would square root both sides. On the side with the number, I put plus or minus, and I get x equals plus or minus 3. So we're going to use that same procedure with a trig function. Tangent squared x is the same as tangent x squared equals 3. So to cancel that square, I can square root both sides. And I still need a plus or minus on the side with the number, the opposite side of the variable. And the square root and the square cancel out. So we end up with tangent x equals plus or minus the square root of 3. Now that happens on the unit circle when you have plus or minus a radical 3 over 2 over 1/2. So we need the y coordinate to be root 3 over 2, the x coordinate to be 1/2, and it could be positive or negative, so that could be in any quadrant. And that happens up at pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So those would be our answers. The next example is similar, but first we want to isolate cosecant squared x, so we add 4 to both sides. And then we square root both sides to cancel the square. Don't forget the plus or minus. And we get cosecant x equals plus or minus 2. Now remember that cosecant is the reciprocal of sine. So if this is 2 over 1 and I flip it, I could find where sine x is equal to plus or minus 1/2. Sine x is equal to 1/2 at pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Well, at 7 pi over 6 and 11 pi over 6, it's negative 1/2, but we do have plus or minus. So since we're searching for our answer between 0 and 2 pi, our answers are pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Here are some more examples of solving trig equations that are quadratic in nature, and we're going to be using factoring and the zero product property. This first example is already in factored form, so using the zero product property, I can set this first factor equal to 0, cosine x equals 0, or the second part could equal 0, 2 sine x plus 1 equals 0. And I'm going to solve both of these equations to find my answers. In the first part, where does cosine x equals 0? That's at pi over 2, and also down at 3 pi over 2. So I get those two answers from this first factor. And then I also want to solve the second equation. This one I have to isolate sine x. So I subtract the 1 from both sides. 2 sine x equals negative 1. Divide both sides by 2. Sine x equals negative 1/2. And sine x is equal to negative 1/2 at 11 pi over 6 and 7 pi over 6. So for our final answer, we're going to join all those answers together. The final answer for this problem is we've got pi over 2, 7 pi over 6, 3 pi over 2, and 11 pi over 6. The next problem, 2 cosine squared x minus 7 cosine x plus 3, reminds me a lot of the equation 2x squared minus 7x plus 3 equals 0. And it's really the same thing, but instead of x, we have cosine x. So if it helps for you to solve an equation in this form, first, go for it. I'm going to put two sets of parentheses, and 2x and x are going to multiply to 2x squared. I'm going to need a 3 and a 1 to multiply to 3. And since my inners and outers need to add to negative 7x, I need these both negatives, so we get negative x and negative 6x, which combines to negative 7x. Now back to the original equation. Two sets of parentheses equal to 0 on the other side. I'm going to put 2 cosine x and cosine x, and again a 1 and a 3, both minus. The inners multiply to negative cosine x. The outers multiply to negative 6 cosine x, and those do add to negative 7 cosine x. Now to solve this using the zero product property, I solve 2 cosine x minus 1 equals 0. Add 1 to both sides. 2 cosine x equals 1. Divide both sides by 2. Cosine x equals 1/2. Cosine x equals 1/2 at pi over 3, and also down at 5 pi over 3. Now we also have to solve the other part of this equation, cosine x minus 3 equals 0. So I add 3 to both sides and I get cosine x equals 3. Now I can't think of anywhere on the unit circle that cosine x equals 3. And if you remember when we graphed cosine functions, they oscillated between negative 1 and 1. So the range of a cosine function is negative 1 to 1. Therefore, cosine x could never equal 3. So this part has no solution. So that part of the equation just doesn't give us an answer, and our only answers are going to be pi over 3 and 5 pi over 3. Now, for our last equation, solve for theta in the equation 1 plus sine theta equals 2 cosine squared theta, given theta is between 0 and 2 pi. Now this one, I have a cosine squared, but then there's a sine. The fact that it's not uniform, where I'm only dealing with sine and only dealing with cosine, makes this seem tricky. So I'm going to see if I can use a trig identity to replace cosine squared theta and get a different expression in there. So remember our Pythagorean identity, sine squared theta plus cosine squared theta equals 1. If I move sine squared theta over to the other side, I get cosine squared theta equals 1 minus sine squared theta. And so what I'm going to try is replacing cosine squared theta with 1 minus sine squared theta, so that my equation only has sine thetas in it. And we end up with 1 plus sine theta equals 2. And then here's where I'm inserting 1 minus sine squared theta in the place of cosine squared theta. And now I'm going to distribute and try and get my terms to one side. 1 plus sine theta equals 2 minus 2 sine squared theta. Now I'm going to take both of these terms and move them over to the left side of the equation. So I'm going to start by adding 2 sine squared theta, and it will end up as positive 2 sine squared theta on the left-hand side. And then I'm going to copy down the sine theta that's already over there. And then I'm going to subtract the 2 from both sides, and we end up with minus 1 on the left-hand side equal to 0. And now we want to factor. If it helps for you to go off to the side and do 2x squared plus x minus 1 equals 0 and factor that, we get 2x and x, 1 and 1, plus here minus here. This equation is going to factor similarly, but it's going to be 2 sine theta and sine theta, 1 and 1, a minus and a plus. Now I want to solve my two equations. So 2 sine theta minus 1 equals 0. I add 1 to both sides. 2 sine theta equals 1. Sine theta equals 1/2. That happens at theta equals pi over 6 and 5 pi over 6. And then for the other part, sine theta plus 1 equals 0. Subtract 1 from both sides. Sine theta equals -1. That happens down here at the bottom at 3 pi over 2. And so combining all those answers, theta can be pi over 6, 5 pi over 6, and 3 pi over 2.